Yeah. Hello, everybody. So, thanks for coming. Thanks for coming to this conference. It's been a while for me. I remember we coined the term kernel speech somewhere early 2020. So it's nice to see a full conference dedicated to that field. At the time, we basically did. I can be honest about that. We did probably the first annual field quantum computation, which was actually a small IBM at the time. Okay, so today I'm going to basically start to sort of split up into two parts. The first part is about quantum pictorialism, which is a new language for quantum, and because that's actually the underpinning on how we get to something that's scalable, interpretable, quantum AI. It's really the essential ingredient of the whole thing. And I'm going to start with the language of quantum. So the language of quantum, by which I mean the Hilbert space form, which everybody uses, is due to John Neumann. As probably most people know. Now, what everybody know, I guess, is that von Neumann, who published this language in a book in 1932, denounced the Hilbert space formalism in 1935. So it's quite an uncommon thing that somebody who creates something like that 3 years later just throws it in the bin. And that we hear in the first day talk this morning, we hear people mentioning about quantum logic, and then this sort of breakdown of distributivity. That was actually von Neumann's first attempt to come up with an alternative quantum formalism. Okay, I'm going to be quick about that. So this is Schrödinger, and of course you know him from his cat, from his equation. What you may not know is that Schrödinger said also in 1935 that when two systems enter into temporary interactions, I would call that one the growth of decharacteristic quantum mechanics. What he means by this is that if you're going to understand quantum mechanics, you should focus and zoom in particularly on the composition of systems, which goes against what actually von Neumann found, except you need to zoom in on the measurement, quantum measurement. So, and all the philosophers and everybody has done that, and everybody is trying to come up with a new quantum formalism has always focused on the measurement. So, Schrödinger has focused on the composition of systems. The fact that the whole is not being derivable anymore from the part. If you got an entangled state, a perfectly entangled state, and the part is just noise. How are you going to get from noise a description of the whole? It's just impossible in 90%. So this is Penrose, also from Oxford, in mathematics. So I'm based in Oxford. I don't know whether I mentioned that still. Among all the things Penrose did, one thing he did when he was still an undergraduate, holding it upside down. Is it open? Maybe I didn't put it on. Let me check. No, oh, yeah, it is. So Penrose, when he was an undergraduate student, he really hated the stencil notation, which you have to learn for general relativity. And instead of using that notation, he started these blobs where the superscripts became like input wires, and the subscript became input wires, and the subscripts became output wires. So that was his, so he preferred his pictorial notation of the tensor notation. Now, so von Neumann wanted the new quantum formalism. Schrödinger said quantum is about composing stuff. Penrose used pictures instead of symbols, and it turns out that the last two here, they're one and the same thing. Like if you want to start like a language for anything, a formalism or whatever, which focuses on composition of systems, then you naturally end up with a diagrammatic language. And this is something that comes out of the field of mathematics, which is called model category theory, which I'm not going to go into, but that's where it sort of came out to. Anyway, so I started working on this idea of building a new quantum formalism focused on composition, which also means like focused on pictures in 2003-ish, and then in 2017, Alex Kissinger and I, we published this book, Picture Quantum Processes, which by then had been like for 5 years the Oxford computer science course for quantum computing and quantum foundations and everything in computer science. So this is basically a textbook of a course, and it gives you an entire course of quantum theory using this pictorial language. So this is another book which I wrote much more recently with Stefano Bobbiosi, from what I understand, gave a course here at at Indiana at some point a few years ago. Was somebody there? You know Larry Moskos. I know Larry Moskos. Yeah, so he gave a course at Indiana about this sort of stuff a few years ago. Now, what's the difference between this book and the previous book? Well, it's written on the back. Hello there, want to learn some quantum? Maybe you think you don't know enough maths. Well, that's not the problem. The picture in the book are new kinds of maths. They're not the watered down maths, they're new kinds of maths. We teach you all about the quantum world. And so he publicized this book, and then you see this whole page, there was a whole page in the Guardian, and they said like this book, it's easier to convince kids than adults about quantum mechanics. I mean, I can go into educational philosophy and stuff like that to explain that, but rather than that, I'll show you what we did in an experiment, briefly, because that's not the center of the talk, of course. But so basically, we have this book, and we consider this as a textbook for a course. Then we basically record lectures for this book in my office, and we basically had 8 lectures covering the entire book. Then we create some exercises, with exercise solutions. And essentially what I'm doing here is I'm giving all the ingredients of a course, a quantum course, which we gave at Oxford now 2 summers ago. And we invite kids in the UK for ethical and legal reasons and whatnot. This could only be in the UK, like teenagers in the UK, high school students in the UK. And I said, hey, you can come and get, well, not come, you can take a free course this summer, and if you take it, then you get a certificate. Doesn't matter how well you do, doesn't matter. You take the course and you get a certificate. So we got about 1,000 applications. We, as random as we could, select 60 randomly to do with what school are you coming from, what is your interest in science versus humanities, and then of course gender and ethical backgrounds, whatever criteria you want to randomize. So that we really get a nice cross-section of UK high school students. So okay, they took the course. Now, what they didn't know was that at the end we asked them, so hey, we've got a few exercises here, can you solve them so we can learn how well we did? So it's not we are not examining you, you're examining us more. So we gave them these exam questions, and they turned out to be all questions from Oxford University postgraduate exams. The whole way the course was set up with 8 lectures, like 8 weeks, 8 lectures, exercise sheets every week, 1 hour tutorials also every week, like with groups of 12 or something like that. That's exactly the structure of Oxford University postgraduate exam course and exam. That's exactly it. So we mimicked the Oxford University postgraduate exam, and we gave them a postgraduate exam at the end of the course, and 50% of the kids got distinctions. So I mean that's. I mean, the paper is only out recently, that's of course, that's what was reported on here in the Guardian. Okay, so there's a new language, I'll give you some more data because people are kind of are interested. Just check how much time they spent a week. Like the majority between 1 and 4 hours, and this already included watching a lecture and attending a 1-hour tutorial. So they didn't really do much more than that. They're trying to solve their exercises. This is also nice. You have state schools and private and boarding schools, really no different. They're all around 60% on average. So the background didn't matter. And you see, people not necessarily have an interest in STEM, they're all very interested, more interested in STEM. And one of the coolest things, we had also like an open question, like, what else do you have to say about this? Just say something. What the majority said, it was fun. They didn't say it was interesting. I mean, they found it interesting, but they especially pointed out that it was fun, which is important. Okay, now let me give a taste of what like the language we use. Then it's based on what we call spiders, and to understand a spider, you need to understand a wire. So what is a wire? A wire in the abstract is a thing that connects 2 endpoints. Right? That's a wire. Now, what is the behavior of a wire? Well, if you connect 2 wires together, you get again a wire. I mean, just think an extension lead or something like that. You connect 2 extension leads together, you get again an extension lead. Nothing new. Now, what is a spider? It's like a thing with not necessarily 2 ends, possibly multiple ends, or 1, or even 0. That's a spider. But it's essentially like a wire, because if you connect 2 spiders together, you get again spider. That's basically I mean, I can't go into the mathematics. There's a lot of mathematics here going on behind the scene, highly non-trivial mathematics, and you can basically prove that this, I mean, don't try to understand it if you don't know it, because I think it took us like 4 years to basically build that up. So if you don't do this like, this, for those who know what an orthonormal basis is, this essentially is the definition of an orthonormal basis, the way you've never seen it. And that's how this connects to, say, quantum mechanics. This, you have to think of this as a quantum measurement, a quantum observer, or whatever characterizes it. That's what you think of. Okay, so these spiders correspond with, if you want, to quantum observables or a quantum measurement or something like that. And so we actually have two kinds of spiders around in our language. You see, you got the green ones and the red ones. And the rule for these is not that they fuse together. The rules for these is that they basically each give each other an uppercut. You see, one gives and then these legs fall off because spiders, their legs are not very strongly connected to their bodies. So whenever you put two wires between the spiders, then they hatch. That's the rule. So I'll repeat, same color, they just fuse, different colors, two legs fall away. Okay, now let's do some quantum computing. Quantum program. So this is a quantum program. So how is this quantum program? These are 3 qubits. So 3 qubits. And I mean, it's like a quantum circuit. Huh? And then the things here, they actually turn out to be C0 gates. If you pick particular, I told you that these things correspond to certain bases. If you pick particular bases, this is the Z basis for the green, the X basis for the red, and you get exactly a C0 gate this way. Turns out. Okay, now we want to simplify this program. What do we do first? I've told you the rules. The first thing you do is forget that it's a quantum circuit. And you just think of these as a bunch of spiders. That's the first thing you do. What do you do next? I gave you the rules. Huh? I don't hear anything. And same color they fuse, right? Same colors fuse. And same colors fuse, boom. Okay. What do we do next? 2 wires between red and green, they vanish. And now we've got a spider with 2 legs, so that's just a wire. So we actually simplify this quantum circuit. Now this is a very simple example. This is the state of the art. Like if you go, for example, to the Quantinuum compilers, and many other ones, how you simplify a quantum circuit. This is state of the art, using these spiders. This is about much better than any other technique to simply. This is now also very standardly used in quantum error corrections and many other fields like in quantum engineering, basically. Also, I have a simple that example is. Conceptually, like one of the difficult things in quantum is quantum measurement. Just as an historical fact, because it was alluded, this quantum logic was alluded to this morning in the first half. So the failure of that program, which was a program started by von Neumann, was that von Neumann conceptualized quantum measurement, but wasn't able to derive from that how you compose systems in an elegant conceptual way. What we're going to do now is we start this from the idea of composing things. We're now going to say, how do measurements live in this language? And it's very simple. So we're going to do a slight change of convention. From now on, when you see 1 wire, you think classical. When you see 2 wires, you say quantum. So quantum is really a pair of wires which you draw close together, so you know that they actually are connected in some way. But again, if you know density matrices and you don't know what to do tonight, try to imagine how density matrices are in presentation of this thing. You know, density matrix, you always write a cat and a bra. These are actually these 2 things. That's where it comes from. Anyway, so we got 2 wires for quantum, we got 1 wire for classical, we got a process here from quantum to classical. What is this? What is the quantum mechanics process from quantum to classical? It's a measurement. This is a measurement. This is your measurement. There's nothing more to it. You don't need spectra of joint operators, nothing like that. This is your measurement. So this is the opposite. You got some classical data, and you encode it as quantum data. So this is like you have a bit here, and you code this as a qubit, like a qubit data. Huh? And now we can start computing. You first encode something, and then you measure it. What happens?
Collapse.
Huh?
It collapses.
Collapse.
The same colors. It's already in a state of startness, so there's no collapse. Nothing. If you encode in the same basis that you measure, nothing. Now, if you encode in a different basis than you measure, then there is collapse and stuff like that, non-determinism going on. And for that reason, we see two wires in the middle, they just vanish. Two wires just vanish. And this means whatever comes in is not at all connected to whatever goes out. And that's because of the collapse, which is non-deterministic and all of that. Now you can go further. So basically, you can do whatever computation you want involving measurements, circuits, lots of stuff, measurement-based quantum computing if you want to do that, whatever, just with this language of spiders. You don't need anything more. Right, so in fact, so this is Von representing von Neumann's formalism. Any equation you can derive in Hilbert-space formalism of quantum mechanics, the usual formalism of quantum mechanics, you can derive with the rules in this book. There's nothing more you can do with Hilbert-space equationally speaking than what's in here. So it's an equivalent formalism for quantum. Okay, let's be clear. If you want to do quantum formalism, we have one. Well, kids can do it. It is completely respectful of Neumann. That's sort of the model theory way to say that whatever equations you can derive in some new language, you can derive in a model and vice versa. That's called completeness in a model theory and logic in general. Conceptually, it follows Schrödinger, and it's widely used in quantum industry now. It's very widely used, but if you talk to the people here from IBM or so, they'll tell you lots of people at IBM are now using this language for many different things. Okay, so now we're going to complete, not change subject at all, but now we're going to go into AI. So far, but I mean, it was about the reasoning that I was talking. It was about some sort of new quantum logic. So in the old days, people would have said, yeah, that's part of AI anyway. But let's now go a little bit more direct into quantum AI. So last year, in 2024, the Quantum Insider published what they thought the 10 best research achievements was of 2024. What I'm going to talk about is now one of them, the one due to us. So there were two Quantinuum entries there. The one was the topological qubit. Microsoft is not here, no? Microsoft, and then the other one was the work I'm going to talk about now by my team. Okay. So this is about actually a new kind of AI paradigm, more specifically a new type of paradigm for natural language, and we call them text circuits. I mean, this goes back 5 years. So today, it was mentioned, there were quite a few talks today already that my name was mentioned, and they were typically talking about something called DisCoCat model of natural language. So when we use this DisCoCat model of natural language to at some point basically do the first quantum natural language processing on quantum hardware, and then we also released this software called Lambek. So this was quite widely covered for a while. So why would one do natural language processing on quantum computing? I mean, a lot of people, they say, okay, throw just quantum and everything is going to get better. That's a pile of crap, that's not true. Something will get better with quantum if there is some sort of natural fit between quantum and the problem. Otherwise, quantum is not going to help you. And this is the case, if you go to the big book I showed, we show, for example, well, this is the generic form of quantum algorithm as a picture, and then there's not much you can do. You do one thing with it, you get Shor's algorithm. You do another thing with it, you get like Grover's algorithm, and there's not much more you can play with it if you really follow that sort of pattern. Now, what happened in 2004? In 2004, I started to work on this formalism for language, for quantum, sorry. And then this, what you see here, was sort of my derivation and description of quantum teleportation. So a very easy way to think about quantum teleportation, just with wires. So, and I was presenting this in Montreal at McGill in 2004, and my friend Jim Lombeck was in the audience. Jim Lombeck, if you went to the talk today, you get a lot of Lombeck too, I think. So that was actually the software they were referring to, the software which was named after this guy, and then usually his name is spelled with a K, and it's now a Q. But anyway, so I was giving this teleportation thing. I said, okay, here's quantum teleportation. Lombeck was in the audience, the father of mathematical linguistics, and saying, well, this is grammar. And because he recognized the mathematical structure here in twice was exactly the same as a kind of grammatical structure, grammatical way, theory of grammar, which is called preluders, and which formally in this language of category theory exactly the same. So he was right. This was like spot on, this correspondence between like quantum structure and language structure. When you see this, you say, oh, maybe quantum computing can do something for us. Now I should say, this is 2004, this DisCoCat was 2008, and I told my collaborators at the time, like, okay, so that was, okay, let me give the history of the problem. I think that's quite important. So the problem was, there were these theories of grammar which go down to long back 19, even further down to Polish School of Logic, 1930s, 1940s, 1950s. So long back really like got it all together. Chomsky, of course, followed up on that, and there was quite a few names. It's gone a long time back. And then at the beginning of say 2004, 2005, some people started to use vectors to represent meanings and started to study them, like what ChatGPT and all these things use, of course. And they say, okay, we can represent words by vectors. We as humans, we put words together to form sentences. And that's something we do. And then, how do we do that? What is the mechanism going on in our head which combines meanings of words in the meaning of a sentence? Something we as humans naturally do. We're not taught how to do it, we just do it. Or we learn it one way or another. So what is the mathematics going on behind that? And the complete question is, I've got a bunch of vectors for words, can I produce a vector for the whole sentence? Of course, I'm going to have to make use of how these words are put together, which is something we call grammatical structure. So given word meanings and grammatical structure, can you produce the meaning of a sentence? So I mean, I didn't know anything about natural language and stuff like that. I never learned anything about that. The only thing I knew from one was that basically my quantum formalism had exactly the same structure as grammar. Now, what flows in the wires here of these quantum pictures? Well, that's vectors. So it was then a straightforward thing to try to use these quantum diagrams to basically see whether they can mediate the vectors and make them flow, and then we could spit out the meaning of the sentence. And the diagrams you've seen today in several talks, which mentioned DisCoCat, they had all these diagrams, and that's literally using these teleportation diagrams. You probably saw them in the talks today, to use this as a way to take the vector meanings of words and then spit out the meaning of the sentence. So lots of people have done this meanwhile, but this is where it came from. So there was this natural match between language and quantum from the start, because we solved these linguistic problems using quantum formalism. This new quantum formalism. You would never have thought about that if you were using your own space. Never. It's because this new language of quantum that you actually think about this and trying to do this. Okay, so here is just a few papers from the time, from around the time. So with Medusa, Zadea, Steve Clark, we first put forward this new model of language, which we call DisCoCat. At the time, we had nothing quantum computing in mind. This was really to deal with this problem of like decomposed meanings in the ordinary theory of meaning in natural language or something like that. Now in 2016, I had a PhD student, Will Zeng, who's quite well known in the quantum community, and as part of his PhD, he actually did ask the question, suppose you do this with a quantum computer, do you get some advantage? The answer was yes, you get some advantage, subject to assumptions like quantum existence of quantum grammar and blah, blah, blah. This was actually a motivation to maybe we should start considering quantum implementation, because, I mean, you see, at the time, I don't know whether, yeah, at the time after his PhD, he really went to Rigetti, and quantum computers started to come about, literally. Then in 2020, Elias Kahn, who's the founder of Cambridge Quantum, and also of Quantinuum, he came to me and he said, hey, guy, he had seen that paper, hey, you should do this on a quantum machine, try to do this. So it's too difficult, the machines can't do it. So we tried to do it, and we actually could do question answering on a quantum computer early 2020. And it was a very small, noisy IBM machine. It wasn't like a top of the line or anything like that. And then we realized like all the software we developed to do this and do more, we kind of released this as a library called Python library called Compact, named after the linguist Lambert. Okay. Now, so this was what I would say our previous approach, our previous theory. And in 2020, at the time, I also proposed a new theory of language meaning and composing language meaning, which was derived from the previous one, but which had a lot of advantages. The main advantage is all these grammatical theories, like from Lambert and from Chomsky and all they did was teach you how to put words together to form a grammatically correct sentence, or how to generate a grammatically correct sentence in generative grammar or something like that. That's what they did. Now, we as people, we're not very interested in like sentences on their own. We usually have texts or paragraphs or descriptions or whole books or something like that. And in the DisCoCat way, there was just no way to compose sentences into text, because the sentence itself was a vector in like a big tensor space, but it was just a vector. And then, what do you do with a vector? How are you going to compose vectors into text? So there was a simple construction I did in this paper, and it's basically like changing the DisCoCat diagrams in a bit, like playing a little bit with the times, such that you can actually start composing them. Rather than doing this derivation, I'm just going to explain to you how to think about language as circuits, like dialect. Okay, so here we got a little text. Now we've got three sentences. Alex meets Bo, Bo marries Chris, Alex meets Bo. I mean, a little bit of drama going on there, yeah? A little bit of drama going on there. And I'll say this is a natural circuit depiction of this simple text. You've got three people, Alex, Bo, Chris. And by the way, before I was reading from top to bottom, now I read from bottom to top, now I read from top to bottom, because that's how we read, you know. You see, the text goes from top to bottom, so this goes from top to bottom. Okay, you've got three people. You see, think of them as like qubits or something like that. That's a qubit state, that's a qubit state, that's a qubit state. You see, they're disentangled. They've got nothing to do with each other in the beginning. They don't know each other, they've got nothing to do with each other. Then suddenly Alex meets Bo. That's like an entangling gate. They get entangled. So what comes out, in principle, would be an entangled state, because they're now an entangled pair, because there's a clear connection. But then can Bo marries Chris. Okay, they're really entangled, very entangled. So this entanglement is probably a lot more than that entanglement. Now everything's entangled. The result will be all three things entangled in some way. And then, okay, you get it all together, and you can see you can go on like that. So as it turns out, you can turn all of language. It doesn't matter which language in such circuits, like adverbs, all linguistic grammatical types you can think about. You can turn any text in such a circuit. Now, I mean, initially, like my goal at the time was simply just composing sentences. I'm literally composing sentences here. Now you see sentences, and I'm composing them. And then when we start to think more about this, so here you see like a little bit more complex. It's actually a single sentence. It doesn't matter as a circle. It's like you can try to read Alice sees Bob dance clumsily and laughs, and it happens to be that Alice is sober and Bob is drunk. Now you can form this is the circuit which captures the meaning of the situation. Now you can say this in many different ways. Sober Alice, who sees drunk Bob clumsily dance, laughs at him. Or you can say, Alice sees Bob dance clumsily. Alice laughs at Bob. Bob is drunk, Alice is sober. Both texts convey the same meaning, but of course they are differently structured. The circuits for both is exactly the same. Now, say it's in a different language, where word orders will be different, and so we saw this in our text, in our presentations earlier on Hindi. The word orders are different than in English, for example. These circuits don't care. All the things like all the typings and the difference between different languages, word orders and stuff like that, they all vanish. So it's kind of a much more compact representation of language than language in terms of like a string of words. Now, I mean, my interpretation of that is that these circuits are much closer to how we cognitively perceive a story in our head. Now, unfortunately, we are like physical beings. We have physical embodiment, unlike LLMs. We do, as humans, have physical embodiment. And when we want to say something, we can only say one word after another. We can't say like the structural circuit. So what do we need to do? We need to turn this information or insert it into words on a line, and there's no unique way to do this, and in different languages people have done this in different orderings. So that's why languages and typings and word orderings are different in different languages, but I think behind it there is universal representation. Chomsky made a big fuss about universality of language and stuff like that, because what they had was, there was a particular algebraic structure in which you can organize define grammatical types and say with formulate correct sentences and stuff like that. And the algebra was always the same for all languages, the algebra, but not the way you implement the algebra for a particular language. That will be language dependent. That's what we call types. The typings are different in different languages. And here you truly have like a representation that doesn't care about which language it is. So this is truly universal. I'm not going to go into all the other things Chomsky said, like language is baked in our head, because I think this is nonsense. This structure is not a structure about humanity, this is a structure of nature. This is just a representation of processes in nature. You can describe situations with it, like for example, if you are watching a movie, you can actually associate with that movie also such a circle. So it's not just about language, it's about like meaning, be it like visual meaning, like cognitive representations and all that. Anyway, so now we actually get what is the connection between language and between text and quantum. We actually now have a strong formal result. Before we had the analogy, which because of mathematical structure, like number 10, we've got a theorem, and we can, under the assumptions of something I call compositional interpretability. Basically, this means compositional interpretability is that if your phenomenon, be it language, be it physics, be it whatever, has a certain structure, an operational structure, certain structure, then you want this structure to be represented in your mathematical representation. In particular, if it has a compositional structure, then you want this compositional structure to be represented in your mathematical modeling of the phenomenon. This is not at all true for LLMs, obviously, because if you take a neural network, the nodes in a neural network have nothing to do with whatever they're describing. Nothing. Here, in what we are doing, the circuits really represent the structure of your language and your text. That's what I call compositional interpretability. If you assume compositional interpretability, you assume machine learning practice, which is really saying you use vectors and stuff like that to represent meanings, then you can formally prove that you will end up with a quantum mechanical formalism. You can prove that. This is my necessity of quantum mechanical description of text, if you want to use machine learning techniques. So that's a very strong result. This is not published. You don't find this in any papers. I haven't written this down. I didn't have time. I was too busy building quantum guitars. Anyway. So now, I said before, we had this result relying on quantum random, that you get some groove speed up for certain tasks if you use the DisCoCat. So in this paper, from last year, I'm going to show the technical slides. So we actually studied like particular algorithms for this text service. We said, let's do question answering. For example, you've got a detective novel. You've got a detective novel, like Poirot or whatever. You run it, you read it, and then the question is asked, like, who's the murderer? And that's question answer relative to the text. You ask, like, who's the murderer? Something like that. So, and in this paper we showed that when you want to rely on the previous theorem, that you necessarily end up in a quantum formalism when you want to have an interpretable model. So if you assume this interpretability as a condition, then you will get question answer is a BQP half, which essentially means you get exponential advantage for this task on a quantum computer. Which is serious. It is serious. Exponential advantage. There is this condition of interpretability, but that's what the world wants. The world doesn't want black boxes anymore for AI. They want interpretable stuff. So in this domain. So that's one result which we have. That's for me. And meanwhile, we have much stronger results, but they are not published yet. Okay, I think this is the coolest thing. So we basically
did this. Now on Quantinuum high-tech quantum computers, we did what I was just describing. You take a text, you run it, I'll give examples later of what exactly we did. You run the text, you ask a question. That's what we do. Of course, you first have to train, you have to train your meetings and all that, normally, which is usually expensive. But anyway, that's what we did. But we actually discovered in the process of doing something, some very cool things. And probably the coolest thing we discovered was that thanks to the particular structure which I'm using, this compositional structure of a text circuits, I'll show that again, this compositional structure of text circuits, thanks to that, we enjoy the property which is called compositional generalization. So what does compositional generalization mean? It means that you start training first with small pieces of text, very small fragments of text. Then you try to train again with large fragments of text. Then you do training again with much bigger text. We saw that it doesn't matter, that there is a certain point where your texts are big enough and they are not that big, and after that you don't gain any advantage anymore by going to look at the bigger text for training purposes. Which means that in the end we could actually train classically. We could train on a simple classical laptop. We didn't need a quantum computer for training. We trained on a classical laptop, and then we went to a text which we couldn't run anymore on a classical machine because it was just too big. This blows up exponentially, and requires patience even with the text because if you got all these stems, it blows up exponentially. And that one we stuck on a quantum computer to basically do the testing. So this is what I call compositional generalization. You can train small and you can test large. And for people who know a little bit about the history of quantum machine learning, there was a lot of attention for quantum machine learning over I don't know how many years. So thousands of papers. And then they realized by the end, oh, we don't really have any evidence that you can actually train them efficiently. And there was actually a bunch of results coming out sort of indicating, we may have a lot of problem training and probably we're going to lose everything we're going to gain algorithmically in our training phase. There's no quantum training here going on, so that problem is gone. Problem is gone, you train classically, you test quantum. So that's the compositional generalization, which is a property of what we did. Okay, so then a third thing I think, so I remember people were talking to me about like, oh, there's this thing, ChatGPT. I think it was ChatGPT 4 at the time. So there's this thing, ChatGPT. It's amazing. I don't believe that. And I didn't want to look at it. The first thing I tried, it completely messed up. So what I tried was specifically this example. It's a simple example. Bob walks out, Alice walks out, Daniel walks out, Dorothy walks out. Bob goes in the opposite direction of Dorothy, Alice follows Dorothy. Daniel goes in the opposite direction of Bob, Alice goes in the opposite direction of Bob. Is Alice following Dorothy? So it's a very simple problem. It is very much, I don't know whether you recognize it, but this is very much like fitted to this form of text circuits. Because the walk, walks north, and these are properties, and the following is just an entangling gate. And so this is like very naturally coming out of these text circuits. And basically whatever we got from ChatGPT, it was pretty random. It was 50% right, 50% wrong, which means it was completely random. And the reasoning itself was typically a complete mess. So it couldn't deal with that. So that's why we picked. So as a corpus of text where we did our experiment, we of course used this particular sort of small little corpus with walking and turning around. We also did an experiment with 4 directions, not just 2, but here just 2 with 4 directions. And it's kind of nice that we could do on a quantum computer something perfectly which ChatGPT couldn't do. So that was a kind of an additional bonus of the experiments that we did. So yeah. I mean, if you want to read more about this, there is a blog post by myself and Ilias Kamp. It's called Talking Quantum Circuits, and we explain all these experiments we did in this blog post with all the relevant links. There's another blog post, a more recent one, Lambek Gen 2. That's the new version of Lambek, which deals with these circuits now. It handles these circuits instead of the, but it also handles still the old stuff, the DisCoCat stuff. But now we can also do all the circuit stuff with it. And that's very new, that's actually very new. So what are we doing now? I mean, I gave you this example of, this was like handcrafted data. This was an handcrafted data set and all that was very simple. Now we are doing all of these things with BBC data in collaboration with the BBC. So that's what we're doing now. It's an ongoing project between Quantinuum, UCL, University College London, with Marusha de Tadeo, who's one of the father from models of DisCoCat, and then the BBC, and then we now try doing all that stuff with real data. So that's one step up. And then something else which is even newer, virtual generative stuff. So which is again like a different stepping stone. Let me look. Yeah, pretty much out of time. So I'll leave you with Heraclitus, Leibniz, and Stirling. A new way of thinking. The true quantum logic. Let's put it like that. Thank you.